So we've made it to um, the next section on thermodynamics. We had to talk about some heat and heat transfer, temperature, definition of temperature, but that brought us here to sort of formalize this heat transfer. And that's the whole idea of thermodynamics in itself. It's just the study of heat and its transfer between substances or uh, molecules or solids, things like that. All right. We're going to start with some preliminary things. We're just going to talk about evaporation, condensation first. Then we'll get into boiling, melting, freezing. And then the last little bit will be the formal laws of thermodynamics. So let's start with just some of the basics here with evaporation. As we said before, matter around us exists in four common phases: solid, liquid, gas, and plasma. Although you don't really see plasma often, it is a fourth state of matter, but you're very familiar with solids, liquids, and gases, and that's what we'll talk about mostly here in the first couple of lectures of thermodynamics. Um, the phase of matter depends on its temperature and the pressure exerted on it. So there's two things in here that actually determine which of these phases a substance or any matter will be in. So if you want to change a substance from one phase to another, that requires some sort of transfer of energy, okay? So if we look down here, you can see that if we want to go from solid to a liquid or liquid to a gas, typically if we want to go up the scale, we need to add in energy. So energy would be absorbed by the matter or the substance. If you wanted to go the other way, gas to liquid or liquid to solid, if you want to go backwards, essentially that substance is going to have to give off or release energy. Now, if we think about just the change of phase from a liquid to a gas, especially if we just think about the surface of a liquid, so maybe we have water or something, whatever the liquid may be. If we think about this interface here between the surface of liquid and air, this is one of the two transfers we're going to talk about is evaporation. And this is just the change of phase from liquid to a gas. So we're going to go this way. We're going liquid to gas in this first instance. For the second half of this particular lecture, we'll talk about going the other way, vapor to a liquid. As we said, the temperature of any substance is related to the average kinetic energy of its particles. Okay, so you'll probably remember that from, I guess, the last module. So the average kinetic energy is related to the kinetic energy, or the average temperature is related to the kinetic energy. Might have misspoke there. So the molecules at the surface gain kinetic energy by being bumped from below. So before any sort of molecules leave, maybe the surface of this water, if we have some H2O, this is H2O, by the way, so this is water. If these molecules get hit from below, so maybe we have some more molecules coming up, there's going to be a kinetic energy transfer, right? So we're going to add some kinetic energy to this upper molecule. So if that energy transfer is large enough, essentially molecules near the surface may break free from the liquid. And you can see that here with these three molecules already. We have 1, 2, 3 actually getting kicked out of the water just because the molecules below them have so much energy. So these molecules will essentially leave the surface and escape into the air above. And this is where they become essentially vapor. So maybe you've heard of the phrase water vapor. And that's essentially just molecules of water in the atmosphere that are essentially acting as a gas within the air that you're interacting with. So the increased kinetic energy of these molecules, um, when they break free, all the energy comes from the other molecules in the water. So if you think about it, there's going to be some sort of energy transfer, not just in the molecules, but between the water and the air. So as there's an energy transfer to molecules in the water, that energy and those molecules get pushed into the air. So there's also an energy transfer, not just a molecule transfer, but there's an energy transfer between the air and the liquid. So we need to discuss that as well. So the molecules about to be propelled out of the liquid, those are obviously gainers of energy. And then those that remain in the liquid, well, those after the collision, they have lower energy, right? Because they had to give some away. Okay, well, that means the average kinetic energy, because remember, speed and kinetic energy, right? The average kinetic energy of the molecules that remain in the liquid is lowered. Okay, so that means the average velocity of all these molecules still in the water, it becomes lower. And that makes sense because all the fast ones either hit a molecule and slow down, or the fast ones leave and become vapor, right? So either the fast ones down here, they become slow, or you can have fast molecules near the surface that just leave. Um, but overall, the whole point is that the speed or the average kinetic energy of what's left over in the water is going to be lower. All the fast ones are leaving. So evaporation is a cooling process. And I've listed that here in blue as a visual reminder that this water is going to cool down because all the high energy particles are leaving. So the fast moving molecules that break free from the surface, they're slowed as they fly away due to the attraction to the surface. But they're still pretty fast. And they're actually fast enough, even though the water's being cooled, the molecules leaving are still fast enough to actually warm the air a little bit above the water. So you've got temperature going down here and temperature actually increasing a little bit above. Okay, well, let's take this idea of evaporation and apply it to an actual real world scenario. So we have this cloth on a metal canteen here. And the question is, how does wetting the cloth, covering the cloth covering of the canteen, cool the water inside? Now, it turns out that if this cloth is wet, the faster moving water molecules on the outer cloth will eventually break free and become water vapor. Okay, so we'll have evaporation. Okay, coming off the cloth, cooling the cloth down, right? So the temperature of the cloth will decrease. Well, if we get a colder cloth around this canteen, well, that means the heat from the metal canteen will be transferred to the cooler cloth. Right now, those two things are touching, they're not liquids, so that means this is done by conduction. So we have a cloth that's being cooled down, which in turn will cool down the metal canteen. Now, when the metal canteen gets cooler, well, that means it's going to take on the heat of the water that's actually inside the canteen. So we have all these steps, essentially. We can say that the water will heat up the cooler canteen, which will heat up the cooler cloth. Put can here, short for canteen. So essentially, when you look at all the steps, if you zoom out, all you're seeing is energy is transferred from the water inside to the air outside. But it has to go through that metal piece in the middle, the actual metal canteen. And that's essentially, I've never tried this, but if anybody has a metal canteen and a thermometer, you could try it, take some pictures, send it to me. I could use it next year or next semester when I teach this class. Um, but let's keep moving on with evaporation here. So you get the idea that it's essentially a cooling process. Um, if you've ever put alcohol on a cut or something, alcohol evaporates quickly. So you'll notice alcohol will feel really cool on your skin. Um, so that tells us essentially that the more rapid the evaporation, the faster the cooling. And essentially, this whole idea of evaporation and cooling down, that's actually how our bodies cool down. Like for all the exercise science majors in the class, um, you probably know that as you exercise and sweat, you get water on your skin, and as that water evaporates, that actually cools you down. Um, so that's actually a natural way that humans actually maintain a stable body temperature. I have this extra picture over here just as an aside, but pigs actually don't have sweat glands, so that's why they always lay in the mud. They coat themselves in mud, and they use that moisture. As it evaporates, it cools them down. So it would make sense that the rate of evaporation is not only faster, or the temperature change is not only faster if there's a high rate of evaporation, but the rate of evaporation itself is greater at high temperatures, which makes sense because there's actually more molecules with high kinetic energy. Remember the water and the molecules coming out? If you have a high temperature water, that means all the molecules in there have a high velocity, which means you're going to have more collisions and more molecules getting kicked out and becoming vapor. Um, what's really interesting is you can actually have a situation instead of a solid turning into a liquid and then evaporating, you can actually skip all that. Through the process of sublimation, you can actually have a solid that goes straight to the gaseous phase. So from solid, gaseous phase, and then you skip the liquid phase completely altogether. And when this happens, uh, in nature, especially, you can see it sort of happen with snow and ice on sunny days in really dry areas. So, like Salt Lake City, places like that. Essentially, you have solid snow, but there's so much energy in there in those molecules from the sunny day and dry climate. Some of those molecules actually just don't even melt, they just go straight to water vapor, right? So you can see that this probably requires more energy than normal to actually jump through an entire phase and go straight from solid to gas. All right, so that's evaporation with a liquid surface, molecules leaving, cooling the surface. Let's talk about the opposite. What if we have water vapor up top and then it actually condenses, turns into the liquid? And I said water vapor, but really any vapor of anything, any gas, you can actually have it condense and turn into a liquid. So the opposite of evaporation that we're talking about here is condensation. So this is the changing of a gas to a liquid. When gas molecules near the surface of a liquid are attracted to the liquid, okay, so like these, when they're attracted to the liquid, they strike the surface with increased kinetic energy and they become a part of the liquid. So essentially, you're just getting these collisions of the vapor molecules here, water actually hits the surface of the liquid and becomes a part of it. In collisions with low energy molecules in the liquid, um, what's happening, as you can probably tell, um, these water vapor molecules, they have a pretty high kinetic energy. But when they collide with the molecules in the liquid, these have a low kinetic energy. So what happens is we have an energy transfer going the other way. So instead of fast, speedy molecules going out, we have fast, speedy molecules coming in. So what happens is it actually increases the temperature of the liquid, right? Because the energy of the molecules inside are probably lower energy. So as a high energy collision happens, they get an energy boost, which means instead of like evaporation being a cooling process, condensation is actually a warming process. So the temperature of the water will go up. Um, Probably notice this in really humid locations. Um, so condensation definitely counteracts evaporation in such locations. You can feel it on your skin. The air will condense on your skin. That's where the sweat doesn't evaporate. You just get sticky. That's the way I usually describe it. I've lived in a desert climate for like 7 years now. So when I go back home to North Carolina, I fly into Charlotte, and the air inside the airplane is always nice and dry and cool. So as soon as I get off the airplane to the jet bridge, I feel instantly sticky just because the condensation is happening. Um, and that's essentially just being bombarded by these H2O molecules. These water molecules are slamming into you. They have high energy, so they're essentially heating you up. So you're warmed by the condensation of vapor on your skin. And if you've ever been to New Orleans, that's one of the most humid, sticky places I've ever been. That place in Florida. Um, if you get a chance to go and you start feeling that sticky, gross feeling, that's condensation. But if you don't get a chance to go to New Orleans or Florida, you can still experience something similar every time you take a shower. So let's look at this example here. So why is it always warmer inside the shower, even if the water's been turned off than outside? So every morning, when I finish my shower, I turn the water off and I reach out and get my towel and bring it inside the shower. I never get out of the shower while I'm wet. Why is that? Well, for starters, I always feel cold. But why do I feel cold? So we can actually think about this in terms of evaporation and condensation. Um, Inside the shower, you're warmed by net condensation. Okay. So remember, the word net usually means multiple things are happening at once, but just one of the multiple things is sort of overtaking the others. Or if you remember forces acting on an object, you sort of add all the forces together and then all those summed forces act like one big force pointing in one direction. That's sort of like what's happening here. So evaporation and condensation could both be happening, but one of them will be greater than the other. Okay, so that's why I say the net condensation here. Evaporation could be happening, but there's just so much more condensation. What we're feeling is net condensation. Okay, and in the shower, you're warmed by net condensation. The air is warm. It is full of water. It's full of moisture, full of water vapor. Um, Therefore, it makes the process of condensation actually warm. Now, outside the shower, once you're wet, outside the shower, there is net evaporation. Okay, so we're moving straight from condensation to evaporation. Now, once you step outside, evaporation is a cooling process. Plus, you've got warm water. So that's high kinetic energy. That's going to leave quickly, right? So that's going to essentially chill you pretty quick. So just taking a shower, you get to see both sides of this. You get to see the condensation, you get to see the net evaporation. Um, if we think about sort of just day-to-day life and just stepping outside, there's always some water vapor in the air, and a measure of this amount of water vapor is called humidity. However, you probably, if you watch the Weather Channel or you're a weather junkie, probably haven't heard just humidity used by itself. You've probably heard of relative humidity, which is usually what weather reports use. So the whole idea of relative humidity is essentially this is the amount of water vapor currently in the air compared to how much it could actually hold, right? So if you have a box, we'll say this is a box of atmosphere, ATM, you got a big box, but it's capable of holding a lot of water, but maybe we just have, ooh, I should change this to blue. There we go. Maybe we just have a little bit here. Right, so here's the water. So maybe it's only 25% full. So that means in the atmosphere, 25% of it is essentially, this is this is overly simplistic, but if you think about the atmosphere and how much water it could hold, in this case is holding 25% of what it could hold, and that means the relative humidity is 25%. Now, what changes the size of the box is the next question. So box size. It turns out the temperature changes that, right? Because whatever the temperature of the air is outside, if the temperature will dictate how much moisture the air can hold. But the main thing to take away from this is that relative humidity tells you at some given temperature um, how much water is actually in the atmosphere compared to how much it can actually hold. Um, if you ever hit essentially 100% relative humidity, that essentially means that the air contains as much water vapor as it can. It's saturated. It can hold no more water. Um, so something you could do if you wanted to see this is essentially you go where the temperature drops, because that's going to lower how much you can hold. That's where water vapor starts condensing. Think about like a really cold morning when you see the dew fall. That's essentially where the atmosphere is cooled enough. And you could think about it like squeezing a sponge out. You're just going to squeeze all the water out of the atmosphere. So that's where water is saturated, or the air is saturated. The air is going to be saturated near the surface where it's cooled, and you get that condensing dew in the mornings. In that situation, usually the slow moving water molecules are the ones most likely to condense and form droplets. And that makes sense because the lower air temperatures, like in the morning, um, so they usually have slower moving molecules, um, which makes saturation more likely. Um, and you can think about that in terms of this picture here. So if molecules are moving fast and jumping around, they're less likely to stick together, right? They're less likely to condense. So if the molecules are moving slower, so lower temperature, they're more likely to smash together and stay stuck together. Okay, so condensation is more likely in this scenario. Um, and you should remember that warm air can contain more water than cold air. Okay, so that's why if the moist air comes in over cold ground, like in the morning, the cold air will sort of act like a sponge and wring that water out. Here's a similar example, but it's something that I'm sure you've experienced if you drink like a soda out of a can. But why does dew form on the surface of a cold soft drink can? Essentially, it's the same idea. Water vapor in the warm air is chilled when it makes contact with the cold can. So if this can is cold, and the air around it is warm, we're going to think about this little this interface here where we have warm, we have cold, right? So this cold on the right hand side is going to start cooling down this layer of air up against it. Okay, now they're slowed, these molecules are slowed down because the air gets cooled. And since they are slower, they can actually start the condensation process, right? So that slow speed of the molecules on the surface there, ooh, excuse me, the slow speed starts building up water on the side of the can. And that's why a can, which is interesting because people say, oh, that can's sweating. But really, it's just condensing water around the atmosphere. So it's not that the can is hot and sweating like people do when they exercise and get hot. It's actually because the air outside is cooling down. All right. Well, we talked about air coming in. We talked about the temperature changes. Let's talk about air going up. So warm air rises, and it makes sense because when air heats up, it expands just like a balloon, and a balloon is going to be very buoyant. So warm air is going to expand and rise, but as it rises, it's also going to drop its temperature. And if you think about it, if air expands, there's going to be, I'm going to draw it. So if we have lots of molecules bouncing around in, say this is a little box of air, okay? If we heat it up, it's going to expand. So now we have all these interactions. It's going to expand, which means there's going to be less collisions, right? All these particles have more room. Okay, and more room means less collisions. Which means a lower temperature. So that's why as air rises, it will chill. Now, as the air chills, the water vapor molecules that were just in there that you couldn't see, they start slowing down, and then they start having collisions and sticking together, right? Okay, because that's what we need for condensation to happen. Condensation needs slow particles. And since there's fewer collisions to exchange energy, it makes sense that we'd have more slower molecules. Now, when water molecules in the atmosphere actually combine with tiny particles of dust, salt, and smoke, things like that in the air, that gives these little collisions and these coalescing molecules, it gives them something to stick to. It gives them essentially a nucleus. Gosh, what's the word? Cloud formation is not my specialty. I'm a terrible atmospheric physicist. Nucleation, cloud nucleation, I think is what it's called. But essentially, that's just the process of where water starts forming on essentially air plumes like dust and other grody things in the atmosphere. But what happens here is you can see if the air comes in and it's got any moisture in it, well, it gets pushed up by the mountains, right? Because a cloud or air can't get through the mountains, so it's going to go up. And we just said earlier that as air gets pushed up, its temperature drops. And of course, there's going to be some dust or dirt or something, microscopic particles that float up here in the atmosphere. So that's actually what you see when you're looking at clouds. You're looking at this condensation process where air gets lifted up, it cools, and then starts making cloud droplets that you can actually see. They're big enough finally after they coalesce to where you can see them. And that's essentially what causes clouds. Um, oh, yep, it's right here. Yeah, so warm breezes blow over the ocean and become moist. They pick up all that water. That moist air moves from warmer to cooler waters, or from warm water to cool land. It chills. Yep, so water vapor molecules actually start coalescing and sticking to each other. So if this process happens and it stays on the ground, it's called fog. If it gets elevated from warm air being pushed straight up, or mountains or something, then you have a cloud. So essentially, cloud and fog, same thing. Just the only difference is how high it is. All right. The last thing I want to talk about, which is very important these days, is essentially the wet bulb temperature and what that means. The question here is essentially, what happens when evaporation can't occur? So we've been talking about sometimes evaporation happens, right? And that's when we go from the surface of a liquid up to the air. Wow, that should be a cube. There we go. And then we've also talked about condensation, where we go from the air to a liquid. Now, with evaporation, this is a cooling effect. Over here, this is a warming effect. Put these in parentheses. So the question is, if humans, when they get hot, they sweat and the sweat evaporates into the air, and that's what cools them. What happens if it gets so hot and the air gets so full of water? So what if we have no, no. What if we have skin and air? So your skin and air, what if you start sweating and you get water on your skin, but what if the air is already so full you can't sweat anymore? That means your body can't cool yourself down. And it turns out, if you get in this situation, uh, I think humans can only last just a few hours if you can't actually evaporate your sweat and lose that temperature naturally. Um, so something that tells us when this happens is the wet bulb temperature. And I won't get into the details of how the wet bulb temperature, like all the math behind it, but essentially all you do is you take a thermometer and you place a wet cloth around it. Okay, so essentially what's going on is you get evaporation in this cloth, and you can imagine that the temperature in the thermometer, is going to go down from, if you just hold the thermometer, set it out there, and take the temperature, you wrap this cloth around it, you wet it. Evaporation is a cooling process, so that's going to lower the temperature. Now, what you do is you think about where the temperature is, what the evaporation temperature is, or the wet bulb temperature is. Now, if your body, or if that temperature doesn't meet a certain threshold, that wet bulb temperature, essentially, once it gets to a certain point, your sweat doesn't even evaporate anymore. Used to, 20 years ago, 30 years ago, climate scientists really didn't talk about this because it wasn't that much of an issue. But now there's parts of India that are getting to this point where it's not livable, it's not survivable on the hottest days of the year, literally because the wet bulb temperature is so high, you can't evaporate your sweat anymore. There's the temperature for that to happen is essentially the threshold is set too high and your body can't get there. So that's something new, something that totally makes sense in this class, given this energy, technology, and society. That's something to think about, and really brings home, I think, the ideas of evaporation and condensation. So on that note, that sad note, I'm going to stop. Next, we'll talk about boiling, freezing, and phase changes. And then after that, the last part of this module will be talking about the formalities of thermodynamics itself. So as always, if you have any questions about anything in here, feel free to email me and let me know. I'll be more than happy to answer any questions.